Now, that was the first method for solving this problem, looking at it as an alternating series. Another way to solve it is looking at it as a Taylor series and using the formula for um, Taylor series, right? So again, going back, we're looking for x or a range for x for which we can use only these terms for our sine x, and the error has to be less than this. Let's go back, write the Taylor series for sine x again. So again, we're cutting off here, but let's go back to the formula for the error. So this is the Taylor series for sine x, but we said if we only use a few number of terms, let's say n terms, then the error Rn is equal to this derivative at a point C, x to the n plus 1 divided by n plus 1 factorial. This is the residual for any Taylor series. If you use n terms to approximate the Taylor series instead of infinite number of terms. Now we can't just right away go ahead and say, okay, I have this formula and I have two terms here. We can't say that because if you remember when we were calculating the Taylor series for sine x, some of the terms were 0 and we ignored them and we found a new formula and wrote it in terms of k, for example, instead of n, and we changed the whole notation that we were using. So in order to use this formula, what we can do is go ahead and find out the derivatives of sine of x. Okay, that's how we were originally finding the Taylor series, right? So now if I find out the derivatives, they are going to be 0, 1, and negative 1. And based on those zeros, I can find out how many terms I actually used to get to these two terms only. That way I find n. After that, after I find n, I can use this formula for the residual for Taylor series and say, okay, this is my error. This error has to be less than the value set in the question. And from there, I should solve for x. So if I find n, I'm sorry, this is factorial here. If I find n and n, and if I find a limit for this one, I get rid of everything, and the only unknown here would be my x. So let's find n. Remember when we were finding the Taylor series for a function, in this case sine of x, we said we start with the function itself or the zero derivative, which is the function itself, then the first derivative, second, third, fourth, and so on. So for the 0 one, n is equal to 0, the function that I'm trying to find Taylor series for is sine x. So for the 0 derivative, I have the function itself, so sine x. The first derivative, I have cosine x. I continue negative sine, negative cosine, sine. And now, remember, when we were trying to find the Taylor series, we found this is the formula for Taylor series that we used, n equals 0 to infinity. Then we had the derivative of that function at point A times x minus a to the power of n divided by n factorial. This is how we found the Taylor series. So now we try to find the derivative at point A. What is my point A? How do I find out? If I'm finding sine of x, and these are my polynomials, because I have x minus 0 here and x minus 0 to the power of 3, my a is 0. So if I had x minus 2 to the power of 3, then my a would be 2. So I know that my a is 2. So these are my derivatives at x, and now my derivatives at a, which is 0, is the first one. Sine of 0 is 0, then 1, again 0, negative 1, 0. So now let's go back to these two terms and how they relate to these derivatives. For the first term, I have 0. For the second term, I have 1 multiplied by x to the 1 divided by 1 factorial. So plus x, that comes from this one. The third one gives me, again, 0. This one gives me negative x cubed over 6. And this last one also gives me a 0. That means if I use 1, 2, 3, 4, 5 terms, or n equals 4, for my Taylor series for sine of x, the polynomial is this. That's because I have some zeros in there. This doesn't mean that I used only 2 terms of this Taylor series. Because I have zeros, this means that I used 4 terms starting from n equals 0. So 5 terms starting from n equals 0, and that means the last n is 4 that I used. So this is, in other words, I'm using P4, which means 5 terms starting at an n of 0. I'm calculating P4 with this term. Okay, now that we found that out, we go back to this formula for the error. So I figured out that when I use this estimation for my sine of x, these 2 terms, I'm actually using 5 terms of the Taylor series, and my n is 4. So I'm using, so this is not the number of terms. This is n, which means 5 terms. So n is 4. So n is equal to 4. And I'm using 5 terms actually. So n plus 1 terms. Anyways, my n, I figured it out. That means everything in here will be n plus 1. Now, in order to get rid of this term here, the n plus 1 derivative at point C, which we don't know, we know that all of the derivatives of sine of x is either sine or cosine. And we know that both of them, so some derivatives will be sine of x and some derivatives will be cosine x. And we know in both cases the absolute value will be less than or equal to 1. Because we're looking at sine x at point C, which we don't know what it is, and cosine x at some point, which we don't know what point it is. But no matter where the point is, that value is going to be less than 1. That means if I look at the absolute value of the error, and I now have the absolute value of x to the power of n plus 1, for this case is 5, divided by n plus 1 factorial, which is 5 factorial. And now this is going to be less than or equal to, because this is less than or equal to 1, this is going to be less than or equal to 1 times what we had, 3 times 10 to negative 4. That's not 1.3. These are multiplied. Anyways, we get to the exact same thing we got before. We solve for x and we find a range for the absolute value of x.